Today I will be expanding on the topic of solubility, in particular, the solubility of gas in water. We will begin with a quick content review from Module 10 of solubility, then we will move on to Henry's law, which describes gas solubility in water. Then we will apply Henry's law with a sample problem for you to pause and try by yourself. For Module 10 on solubility, we have already learned about the solubility of solids into aqueous solutions. For example, we have calcium sulfate, which can dissolve in water and give you aqueous calcium sulfate. The solubility constant is the equilibrium constant for the equilibrium established between a solid solute and its ions in a saturated solution. When writing out the expression for the solubility constant, it's important to remember that solids are not included, as well as pure liquids, in the KSP equation. We only include gases and substances in solution. So for the above example, this expression can be simplified to what is shown on the board. We will now look at expressing just the solubility of gas in water with the use of Henry's law. As previously mentioned, gases are expressed in the equilibrium expression, although we will be focusing on Henry's law in this situation. So water can be considered a universal solvent, and this is because it can dissolve both ionic and polar solutes, and it can also dissolve some non-polar solutes, but this depends on the amount. It has to be very small. So pause the video and try and think of some scenarios where a gas is soluble in water. So there's carbon dioxide, so like in a soda pop or something like that, and you can also have oxygen, which we probably thought of as well, which is dissolved in a body of water like a river, lake, or etc. If you think back to the fall semester when we spoke about polarity, oxygen is a non-polar molecule, so it doesn't actually dissolve in water, but with an alteration in the pressure and temperature, it is able to be forced to dissolve or be soluble in water. Just to further your knowledge on other gases and their solubilities in water, there I have a few. So it's grams of gas dissolved in 100 grams of water, and the total pressure is 1 atmosphere. That's how the solubility is measured here. This is from Wired Chemistry, this information. So it's acetylene and ammonia, carbon dioxide, hydrogen, oxygen, and nitrogen. And if you look on the right side, you can see that ammonia has a very, very high solubility compared to hydrogen. So this one's very soluble in water. And some other ones that are also have a high solubility are sulfur dioxide there with 11.28 and bromine with 14.9. Alright, so now we're going to move into Henry's law, and this describes the amount of gas dissolved in water. So this law states that the amount of gas that dissolves in a volume of liquid is directly proportional to the partial pressure of that gas in the air above the liquid. So the more gas above the liquid, the more gas will dissolve in that said liquid. So the following equation describes Henry's law. It's C is equal to K times P gas. So C is the solubility of a gas in a particular solvent at a fixed temperature. P gas is the partial pressure of the gas above the solution. And then finally we have K, which is the proportionality constant, and it can also be referred to as Henry's constant. So here's just a little diagram. You can see the partial pressure of the gas above the solution. So to determine the K value, you need to have one measurement of the solubility of the gas at a known pressure and temperature. We measure the solubility of the gas in molarity, but you're usually given milliliters of the specific gas in the question per liter, and you use this to determine the molarity of the gas. Then P gas can be measured in various pressure units, but like atmospheres or bars are example. And again, the more gas above the liquid there is, the more gas will be able to dissolve in the liquid. And this relationship is linear for any particular gas, but as always, there are some exceptions. continuing on, there are some limitations that come along with Henry's law. So first of all, it does not hold true for gases that undergo a chemical reaction after the gas is dissolved in water. So for example, carbon dioxide and water react to form carbonic acid. So this does not hold true for Henry's law because it undergoes this reaction after it has been dissolved. Another limitation to this law is that it does not hold true for extreme temperatures, so extreme high or extreme low. And finally, it is only applicable if a system is in equilibria. Alright, so now that you know a bit more about what's going on with Henry's law, we're going to try an sample problem from the textbook here. So at 0 degrees Celsius and oxygen pressure of 1 atmosphere, the aqueous solubility of oxygen gas is 48.9 milliliters of oxygen per liter. Find the molarity of oxygen in a saturated water solution when the oxygen gas is under its normal pressure, partial pressure in air of 0.2095 atmosphere. So pause this video and try and do it yourself using what you just learned about Henry's law. Alright, so we'll begin the question by listing all of our knowns. So we know the pressure of oxygen at 0 degrees Celsius is 1 atmosphere. We don't know our solubility yet, but we can determine that by solving for a molarity. So we know that there's 48.9 milliliters of oxygen per liter, and that is equal to 0.0489 liters. So we can do that times 1 mole over 22.4 liters, which is at STP conditions. And then we know that 1 mole of oxygen can occupy 22.4 liters volume. So then we can divide that all by 1 liter. So if you punch that through your calculator, you should get 2.18 times 10 to the negative 3 moles per liter. So that's your answer for the molarity for C of Henry's law. We can write that out with our other known values, and then next all we need is K to put into the expression. So K we know is equal to C divided by P if you rearrange the formula. So then you can enter those numbers up there, so 2.18 times 10 to the negative 3 divided by 1 atmosphere is your K constant value. So then now you can enter that all into the equation to solve for your C of the oxygen at the normal partial pressure in air. So you can enter your K value and then you can multiply it by the normal partial pressure that it gives you there. So 0.2095 atmospheres, and you should get 4.57 times 10 to the negative 4 for your solubility. This is also an important concept to remember for Henry's law, is you can only use it and apply this law for something involving a gaseous solute in a solution in which the solute is at a very low concentration. To wrap up this presentation, I'll just go over what we went over. So the K constant in Henry's law is determined for each gas, liquid, and temperature combination. Sometimes you can find this in a chart, or sometimes you solve it with the other given information. Then we also went over how the law shows a linear relationship for any applicable gas, and the applicable gas has to be at low concentrations. And finally, we didn't discuss temperature in too much depth, but here's just a little brief concept. So the warmer the liquid is, so for example, water, the less gas it is able to hold. So take, for example, when you're opening up a pop can that's really cold versus very warm. So the warmer the drink, the more likely it is to explode because the warmer water has less ability to hold the carbonation in solution. So when you open up the bottle, the partial pressure of the carbon dioxide, so in the space above the liquid, so the P gas, drops from 100% to well below about 1%, and the carbon dioxide will come out of the solution in the warmer bottle much faster because of the higher temperature. So that was my presentation. I hope it was informative about Henry's law and you're able to learn more about the solubility of gases in water.